quick recap of the concept of chain rule and composite functions that we had seen in the last lecture. And from there, we'll move on to doubts and discussions of any assignment questions or questions from the module as required. Please make sure that you're doing all the worksheet and assignment questions, as well as the questions which are suggested from the exercises of the module, okay, by each of the teachers, and you're doing them systematically in a notebook so that you can refer to them in future properly. And of course, at some stage, there'll be some submissions also we'll require you to do. So make sure that you're doing that systematically. Okay. So as I said, let's start with a quick recap of the concept of chain rule in differentiation. For composite functions. So in general, what we saw is that if we have a function which is expressed as one operation layered on top of another operation, we call it a composite function. This is the general format, you can say, or the general formula of a composite function. So let's take an example of that. Suppose we have y is equal to, let's say, ln of x square plus 2x. Now this is an example of a composite function. So how we know it's a composite function? To calculate the value of y from some given value of x, we have to do two operations. From x, we have to first operate the function g to get gx, and on that we have to operate the function f to get f of gx. So that is how a composite function works. So for example, in this case, from x we have to operate this quadratic function x square plus 2x, and on that we have to operate the natural log function to get finally y as natural log of x square plus 2x. So you can see that when we are operating the function g, we're getting gx equal to this quantity, and on that when we are operating the function f, we are getting f of gx as natural log of gx, which further is this thing. Okay. So this is how we understand from a given function that it is composite in nature, that to calculate the value of y from the value of x, we have to do more than one step. Okay. So whenever we have composite functions, the differentiation is done by chain rule. Okay. So differentiation of such a function by application of chain rule So what the chain rule tells us is that the derivative of this function comes as this final formula. It is f prime of g of x into g prime of x, where f prime and g prime are derivatives. But how does this exactly work? So it comes in a step-by-step process. The first step for this differentiation is what we call the substitution step, where we introduce the dummy variable, let's say z, or you can use any other symbol also, but that z is gx. So y becomes a direct function of z instead of a composite function by doing the substitution step. So in this example, you can see that if I apply the substitution step, I'll substitute z as this quadratic function x square plus 2x. So y will become directly natural log of z. So having done this, the next step that we then apply is the chain rule step, which is that the rate of change of y with respect to x is the product of rate of change of y with respect to z multiplied by rate of change of z with respect to x. Okay. So that will become f prime of z into g prime of x. So in this case, that second step, the chain rule step, it will result in this operation. So now we have to differentiate this ln z with respect to z and multiply it with the differentiation of this, which is differentiation of x square plus 2x with respect to x. So differentiation of ln z we can see is 1 by z, and differentiation of x square plus 2x is 2x plus 2. So the final step then that we're left with is to resubstitute the value of z, because z was a dummy variable introduced by us. So we have to remove that variable and resubstitute it in terms of x. So z becomes gx. So this becomes the derivative of y with respect to x, same as. So implementing that over here, in this particular case, you can see that step 3, the resubstitution, so dy by dx, that will become 1 by z. Now remember what was z? It was x square plus 2x into dz by dx. So that is, we can take 2 common in the numerator here. So write this. So this becomes the final derivative in this particular case, where the example function that we took is y is equal to natural log of x square plus 2x. So for this example function, we got finally that the derivative dy by dx is this by applying the chain rule like this. Okay. So this is something that will take a bit of practice. First of all, to be able to identify a given function as a composite function. Okay. In certain cases, it may not be a composite function. It may be a product, or it might be a quotient, or it might be a simple function. So there, we won't be applying the chain rule. But so the first thing is that looking at a function, we should be able to identify which property of differentiation we have to apply according to whether it is a composite function, or it is a simple function, or it is a product of 2 separate functions, or quotient, etc., etc. Okay. And then of course being able to implement all the steps and with accuracy without making mistakes, etc. So let's concentrate on this application part of it today. Okay, based on everything that we've learned so far. So first of all, a couple of questions I want to discuss. Then we'll come to your doubts from the assignments, etc. We'll come to your particular doubts. Okay. So let's do another example of the application of chain rule. So I hope this part is clear to all of you. If there is any doubt in this, let me know. Yeah, so Bhavika, just to answer your question, when we talk about the exponential function, the definition of the exponential function is y is equal to e raised power x. Here x is the independent variable. Okay. So x can have any value between minus infinity to plus infinity, y becomes a dependent variable. Okay. And E is a constant, which is an irrational number given by the approximate value 2.7. In mathematics also, later you'll learn about this exponential number. There are many different approaches to understanding what the exponential number is. For example, exponential number is actually given by a power series like this. It is 1 plus. Okay. So a series like this that goes on. So it's an infinite series actually like this. That is one way of describing the exponential function. But it's a diminishing set of terms, so its approximate value comes out to be 2.7 like this. Okay. Anyhow, this series is not of concern for us immediately. It's that this is an irrational number which has an approximate value of this much. Okay. So for this function, for example, for x equal to 0, the value of y is 1. For x equal to 1, the value of y is e. This. For x equal to, let's say, 2, the value of y is e square, which will be something 8.78, something like this. Okay. For x equal to minus 1, the value of y is going to be 1 by e, which will be something like this. Okay. For x equal to minus 2, the value of y will be 1 by e square, which will be an even smaller number. Okay. Something like this. Okay. So by looking at this pattern of values, you can also understand that approximately speaking, the graph of the exponential function is like this. This is one of the things that we had learned last time also. Okay. Now, the most important thing about this function is that the derivative of the function is itself e raised by x. This is the unique property that the exponential function has. Okay. So this is the property which is of importance for us in calculus and subsequently in its applications in physics. Okay. So again, to answer your question, Bhavika, e cube is not a function. Na? E cube is a constant. It is just e into e, and e is a constant. So we cannot define derivative of e cube. You're understanding my point? We can define derivative of the exponential function e raised power x at the point x equal to 3, and that will be e raised power 3. But we can't define derivative of e cube itself because e cube is not a function, it is a constant. There's a difference between saying the two things, right? So for example, if I ask you what is the derivative or rate of change of e cube, the answer to that is 0 because e cube is a constant. Okay. But if I ask you what is the derivative of e raised power x at the point x equal to 3, so that is actually e raised power x for x equal to 3. So that is e cube. So that will be something close to about 26 point something like this. So what that means is if I draw the graph of y is equal to e raised power x, and now I plot this point x equal to 3. At that point, if I draw a tangent, the slope of that tangent will be equal to e raised power. This tan theta at this point will be equal to e raised power. So that is the difference between this and this. They are two different things. Okay, so this is very important to understand. Okay. And that's about any function. For example, if I ask you what is derivative of sine pi by 2, the answer is 0 because Sine pi by 2 is a constant which is equal to 1. But if I ask you what is the derivative of sine x at x equal to pi by 4 or pi by 2 or something, then you know derivative of sine x is cos x, and then you substitute the value of x as that. Okay. So anyhow, so let's come to a couple of example questions. So again, this is based on a doubt that one of you asked me earlier, a couple of days back. So we have the function y is equal to e raised plus square root of 2x. Okay. Now we want to find the derivative of this function. Okay. So the first thing is you have to identify what type of function is. Can I substitute it as a product of two functions? No, not really. Can I simplify it in another way as a product or quotient or sum or something? No, we can't. But what we can see is that to get from x to y, first we have to operate the function root 2x. And then we have to operate the function exponential. So you can see that it's a composite function. Now this is your g and this is your f. So we can think of e raised plus square root 2x as f of gx, where f is the exponential function and g is the root 2x type of function. Root 2x we can treat as a simple function because it is basically root 2 into x to the power half. Just treat it like this. Okay. So how will we differentiate? Use chain rule. So this is a composite function. So to find dy by dx, use chain rule. You just apply the systematic steps that we've discussed previously. Okay, and try this out. So step 1, do the substitution. Step 2, apply the chain rule. And step 3, just resubstitute. We should get the answer. Just try this out now. Yes, Anirudh, I'll come to the worksheet doubts also. Okay. We'll do them systematically today. Just give me a bit of time. Yes, very good, Akmal. That's correct. So let's look at the steps over here. So substitution step, you put root 2x as z. Okay. So y becomes e raised power z. So now the chain rule step. Okay. So if this is z, then what is dz by dx? It is differentiation of square root 2x now. So that is root 2 into differentiation of root x. So that is root 2 into 1 by 2 x to the power minus half. So that is, so this is your dz by dx. Whereas what is your dy by dz? It is the derivative of e raised power z. That's e raised power z. Okay. So next step, this becomes e raised power z into 1 by square root 2x. And finally, then after that, do the resubstitution step. So in that, substitute z as root 2x. So dy by dx becomes e raised power square root of 2x divided by square root of 2x. That's it. This becomes our final answer. So hope all the steps are clear. Okay. Now, before we proceed to the next doubt or question, just want to show you something that instead of this, suppose I had an example where I have y is equal to e raised power 2x. Now here I have two options. One is that I can express it as okay, and then I can apply product rule to find dy by dx. Okay. Or the other is I can express it as f of gx, where gx is 2x and f is exponential. Okay. So then I can use the chain rule. So sometimes we have an option in a given question. So for example, if I go by the product rule method, then dy by dx will become derivative of first function into second function plus first function into derivative of second function. So you can see that this will be e raised power 2x, or first let's write the derivative. So differentiation of e raised power x is e raised power x only. Plus same thing. So it is 2 times e raised power x plus x, or 2 e raised power 2x. This is the derivative. Okay. Now if I go by this method, I will substitute z as 2x, and therefore y becomes e raised power z. So next step, so derivative of e raised power z is e raised power z, and differentiation of 2x is 2. So resubstitute and we'll get 2 e raised power 2x. So this is the same as this. But in the previous question, we did not have this option. Okay. Because it was e raised power square root of 2x. So we did not have this option of two methods. There, the only feasible method was using the composite function chain rule method. Okay. Let's move on to another example question, which again Bhavika had asked me. Okay. So this is an example where we'll have to use two rules or two properties of differentiation in the same question. Because you can see that this is the product of two functions. Okay. This is the product of root x, which is a simple function, okay, and 1 plus x squared to the power 3 by 2, which is a composite function. So this makes life a little bit more difficult because you have to use two properties in the same. Okay. So dy by dx, we'll have to use a combination of the two principles. We'll have to use a combination of product rule plus chain rule. When within the product rule, we have to differentiate the second function, we have to use the composite, we have to use the chain rule method. Okay, so just give this a try, we'll discuss. In fact, this is a question from your this thing only, from your module exercises. So in exercise 1, it is there in one of the sections. So just use the hint that I've given you over here and try to work this out, we'll discuss. So first apply the statement of product rule, that it's differentiation of first function into second plus first function into differentiation of second. Now in that product rule, when you are differentiating the second function separately, you will have to use composite and chain rule method to find its derivative. It's a two-step process. Just try this out, people. Okay, so let's come to this question. So what we can do is here, y is equal to root x into 1 plus x squared to the power 3 by 2. So in this, let us treat 1 plus x squared to the power 3 by 2. Let's take this only as z first. Okay, so this will become differentiation of the first function multiplied by the second function, okay, plus the first function multiplied with differentiation of the second function. So here we'll substitute this as z. So it's so this now becomes a separate problem, that z is 1 plus x squared to the power 3 by 2. So what is dz by dx? So now we'll use chain rule again, because this is a composite function. Z is a composite function of x. Okay. So you can see, so we'll substitute. So you can just use some other variable name. U is, let's say, equal to 1 plus x squared. So z becomes u to the power 3 by 2. So the chain rule step now becomes dz by dx is dz by du. So we're just using different names, but rest of the things are same. Plus, sorry, into du by dx. Okay. So dz by du is this thing's differentiation. So that's 3 by 2 into u to the power half into dz by into du by dx is this thing's differentiation. So that's 2x. So that is 3x root u, and we substitute this. So this is 3x square root 1 plus x. So that is now my dz by dx. So having got this, now I will put this back in the original. And we can simplify this a little further. Write it like this, and we can even take 1 plus x squared to the power half common. And then take LCM and on that. Okay. So we will have something like this. 1 plus 7x square right by 2 into square root of 1 plus x square by x. Would be one way of expressing dy by dx. Okay. So we got the value of dy by dx right in this step here only. From here onwards, okay, or this step here onwards, we are just simplifying it further. So this is just a more lengthy version of a differentiation question, because we are having to use two of the properties. Otherwise, there's nothing new in it. It's just that it's lengthy because of that reason. Okay, so hope this question is clear to all. Now let's do a systematic run through of the worksheets if there are any doubts pending first. Okay. So before we come to the module exercise doubts also. So let's go back to worksheet 1 and see if there are any questions pending in that as doubts. Just give me a moment, I'll share that worksheet. So in case there are any doubts, we can go through it. Okay, Kirti has asked for the last question of worksheet 1. So we'll go through that. Okay. So anybody has a doubt in the first question or any part of the first question, please let me know. Okay, what about the second question? Okay. Third question or fourth question? All right, so let's come to the fifth question directly. Oh, sorry, the fourth question, last question. Okay, second one also we'll discuss. Okay, let's go back to the second question. Okay, so Bhavika, what's happening in the second question here is that we have a situation like this, that we have an open cylindrical tank with a given base area, but also it is empty initially. So if we visualize the tank initially at t equal to 0, the volume of liquid in the tank is 0. But we also have an inlet pipe from which water starts to pour in. So the inlet pipe is pouring in water at a rate of 4 cc per second. And this situation continues up to 2 minutes, okay, before the leakage occurs. So for any time now greater than 0 but less than 2 minutes, the level of water will be rising because there is a certain rate at which water is entering, okay, but there's no leakage. So at a general time t like this, you can see of this type, you can see that volume of water will be the rate of inflow so it's a uniform rate into time. So from that we can express volume as a function of time. Volume is becoming 4t in cc per second. And from that we can also express the height because we know the area. So volume versus time and also height versus time, they'll be both increasing like this. Similarly, we can see we can express the height as volume upon area. centimeters per second. Okay. So the height of liquid in the tank versus time, that is also increasing at a uniform rate up to 120 seconds. And when you calculate this, you will see it will become 9.6 centimeters at t equal to 120 seconds. So far it is clear, I hope.
Yes, sir.
Yes.
So can I explain the last part of question number 1?
You mean the C part of the question?
No, question number 1, last part, G part.
Yeah, I'll come back to that. Let me complete this question.
Yes, sir.
So Bhavika, this is clear?
Yes, sir. Now I can solve
Okay.
it.
Now see what's happening in the second part of the situation, that after 2 minutes, okay, the tank develops a leakage at its base at a uniform rate of 8 centimeter cube per second. But at the same time, the inlet is also open. Okay. So now when we take a relook at this situation, what is happening after 2 minutes? So what is happening after 2 minutes is that water continues to come in. Okay. But at the same time, there's also leakage over here. So there is inflow, but there's also outflow, and the outflow dominates. So now the level of water will start decreasing. So after 2 minutes, what is happening is that the rate of change of volume with respect to time is becoming the rate of inflow, which is +4 minus the rate of leakage. So it is decreasing at the rate of 4 cc per second. That means in this graph now, this is starting to decrease and at the same rate as it was increasing earlier. So again, what will happen here, that in this graph at 240 seconds, the volume will become 0, because here the rate of change is -4 and here the rate of change was +4. What it understood?
Yes, sir.
So same kind of thing will happen with the height also. Here the height will be decreasing at the rate of 0.08 centimeters per second, whereas here it was increasing at the rate of 0.08. Okay, because this quantity here, this okay. So now based on this graph, we can calculate anything. For example, the tricky part in this question is to calculate the level of water at t equal to 150 seconds. So we'll have to work this point on the graph. 150 is somewhere over here. So you can see that at 120, it has reached 9.6. And from 120 to 150 seconds, we can see how much it would have decreased by using this relation and calculate the volume at that point of time. Similarly, the average rate or the instantaneous rate of change. Now, because it's a uniform rate, instantaneous rate will be equal to average rate, which will be these kind of quantities. Okay, so from this point, can you complete this question, Bhavika?
Yes, sir. I can.
Okay. So going back to question 1, which part you asked? The last part, the G part, is it?
The G part.
Okay. So let's understand what's happening in this question first. So particle is starting from rest. So U is equal to 0. With its speed is increasing at a uniform rate of 2 meters per second for the first 10 seconds. Okay. And thereafter it starts decelerating at 4 until it stops. So the best way to again do this question is to visualize the graph of speed versus time. So if you visualize the graph of speed versus time, you can see that initially it starts from 0, accelerating at the rate of +2 till it reaches 10 seconds. So when it reaches 10 seconds, its speed would have become 20 meters per second. But then thereafter, what's happening? It's decelerating, and the rate of deceleration now is different. It is 4 meters per second square. So to reduce from 20 to 0, it will only take 5 seconds. So this time should be 15 seconds. Okay, so is this graph clear?
Yes, sir.
So now we want to calculate this thing. We want to calculate the instantaneous speed at 12 seconds. So let's say 12 seconds is somewhere here. So you want to calculate the speed here, let's say, which is v prime at this time, which is equal to 12 seconds. Okay. So what we can do is we can use this relation that from t equal to 10 seconds to 12 seconds, okay, the rate of change of speed with respect to time is -4 meters per second square. Okay. So this unknown velocity v prime or unknown speed v prime minus 20 divided by the time interval, which is 12 minus 10 or 2 seconds, this should be equal to -4. So that will show you that v prime will become how much? V prime will become 20 minus of this thing, 4 into 3, so 12. So it will become 8 meters per second. That will be the speed at t equal to 12 seconds. Okay, that's one way of doing it. You can also do it geometrically. For example, you can see that this triangle that I'm shading here, this one, is similar to this larger triangle, this one. Okay. So you can see that v prime divided by this base. So if this is 12 seconds, so this base is how much? 3. Should be equal to this larger triangle's height, which is 20, divided by the base of the larger triangle, which is 5. That's another way of showing that. Wait, I've got this wrong. This should not be.
It should be 12 meters per second. No?
It should be -8. So, because this thing you can see is 2 into 4, no? So it's -8. So this should be 12.
Yes, now it's clear.
Okay, so hope these 2 questions are clear.
Yes, sir.
Okay. So moving on. Yeah, now 4th question, couple of people had doubts now. We'll discuss it. Okay. So in the 4th question, the first aspect of it you understand is what is the graph given? It's a distance versus time graph. It's a distance time graph. So from distance time graph, what information we know? That slope of it is speed. Okay, so if you look at slope of secant line, it is average speed. If you look at slope of tangent line, it's instantaneous speed. So that is what we have to use to solve all these questions. Okay, this concept we have to use. Now let's observe the graph a little more carefully. Because the graph is the only information I have. There's no other formula, etc. that is given. Okay. So in the graph, specifically, if you see, if you take this point as A, this point as B, and this point as C, why these points are significant? Because the behavior of the graph is changing at these points. From 0 to A, what is happening? You can see that it's a curved graph, okay, such that it's a curve with increasing slope. How I know that it's increasing slope? Because if I draw a tangent, for example, at this point, it's like this. If I draw a tangent at this point, you're seeing the slope is increasing. So that means it is an accelerated motion. Because slope is basically speed. So it has increasing speed. So it's an accelerated motion. On the other hand, if you look at the graph between A and B, you can observe from the graph that it's a straight line. So the fact that it's a straight line means that it has uniform slope. Or slope is the same thing as speed in this case. So that means it is uniform motion. Okay. This next part of the graph here, it's uniform motion. Acceleration is 0. In this part, the acceleration is positive. We don't know how much it is, but we know it's positive. And then similarly, if you look at the part BC, you'll realize it's a decelerated motion. Because if you draw the tangent at different points, you can see the slope of the tangent is decreasing. And here, of course, the slope is 0. So it's at rest after C. So this is the other information that we have. BC is decelerated motion. because it is a curve with decreasing slope. So the slope is the same thing as speed. And after C, it's at rest. So this is the basic information that we get. Okay. Now also, how much is this uniform speed equal to? That is nothing but the, so in this part AB, the uniform speed is actually the slope of the line. So that is distance at B minus distance at A divided by time at B minus time at A. So you can see that that is so 20 meters per second. So at any point of time between 10 and 20 seconds, the instantaneous velocity is equal to the average velocity, or the instantaneous speed in this case is equal to the average speed, which is equal to how much? It is 20 meters per second. So that is the additional information that you are getting from this graph. Okay, so hope all these aspects are clear. Now from this we can answer the various questions. For example, here we want to find out, is the motion decelerated for any interval? So yes, it is decelerated. For which interval? For the interval 20 to 30 seconds. This is the part where it's decelerated. Similarly, it is accelerated from 0 to 10 seconds. What we had labeled as 0 to A first. Now also instantaneous speed at 15 seconds. So 15 seconds is somewhere in between over here. So 15 is between 10 and 20. So instantaneous speed at 15 seconds is actually equal to the slope of the line AB. So that we had seen was 20 meters per second. We had done that calculation just now. Okay. Whereas if I ask you what is the instantaneous speed at, for example, something in between B and C or between 0 and A, the thing is we cannot answer because we don't know what the acceleration or the deceleration is like. So from the graph alone, there's no way to guess how much the instantaneous velocity will be as a function of time up to 10 seconds or after 20 seconds, but before 30 seconds. Okay. So that is why that type of question has not been asked. What has been asked is the average speed between 10 to 30 or the average speed between 10 to 40, 0 to 40. So average speed is total distance upon total time. So next we'll make use of that. So for example, V average from what was it 10 to 30, it is equal to distance upon time. So you can see that at 10 seconds we are here, okay, whereas at 30 seconds we are here. So the distance between 10 and 30 is equal to this much. It is this. It's a distance of 300 meters, but which we are covering in how much time? 10 to 30. So that's 20 seconds. So this becomes 300 by 20 or 15 meters per second. So you can see that this average speed between 10 and 30 is less than the instantaneous speed at 15. Why? Because there's deceleration involved. Similarly, if you look at the average speed between 0 and 40 seconds, this one, you can see 0 is here and 40 is somewhere here. So the total distance traveled from 0 to 40 is the total distance of the journey only, because by the time you come to 40 seconds, you come to rest and you started at 0. So it's 400 meters, which is the total distance divided by the time of 40 seconds. So it's 10 meters per second. So it's even less because now what is happening in this interval, you started from rest. So that is reducing the average speed compared to AB. Then again, you're decelerating and for some part actually of 10 seconds, you are actually at rest. So that's why your average speed is drastically lesser than the instantaneous speed between A and B, or even the average speed between 10 and 30. Okay, so all these types of things before we actually learn differentiation at that stage when we are doing this assignment. So just to give you an idea about how to interpret graphs, how to look at the shape of a graph and understand something about the slope or the rate of change from that, etc. And then subsequently, of course, by the time we came to the second assignment, we learned how to do numerical calculations with respect to these rate of changes using differentiations. Okay, so I hope this is clear. Yeah, Kirti, to answer your question, we could have done that, but for that we have to assume that the acceleration is constant, which we cannot assume over here. Okay, because we are just given the shape of the graph. We are not given that it's quadratic curve, or we are not given the formula of how the S is changing with respect to time. So at 8 seconds or at 4 seconds or something like that, we cannot really predict by that formula also, because we are not given any other data points.
Okay, sir.
Understood my point, but
Yes, sir.
if I said that, okay, assume that the acceleration is constant for the first 10 seconds, then I could have done that. Half AT square would have been equal to this distance. So I would have seen that half into 10 into t square, sorry, half into A into 10 square should be equal to 100. So from that, I'll get the acceleration. So from that, at any other in between time, like 8 or 6 or whatever, I can find out what is the distance, what is the velocity, and all these things. But here I cannot make that assumption, because the question is nowhere saying that we have to assume uniform acceleration in that accelerated part. Okay. So as far as this question is concerned, we have that limitation. Okay, so let's move on from this to the second worksheet. Just give me a moment. Yes, I had discussed the doubts at that stage, but I'm just saying that in case you have revised this and there's anything that you need to understand again, any conceptual doubt or any calculation based doubt, anything you can discuss with me. Okay, so first and second questions are clear, I'm assuming. I think we discussed the second question in quite a bit of detail. Also the third question. Okay. Now, when you come to the fourth question in this, you will see that at that stage, whatever methods of differentiation we knew, we had to simplify these. But now, for example, what we've learned, you can do these questions by using other methods also, like product rule or chain rule or things like that also. So for example, here for this one, we had expanded this, but now you can use another method. For this question, x square plus 1 whole square, you can also use chain rule method. So you can substitute z equal to x square plus 1. So y becomes z square. So dy by dx, you can do it more simply now, is dz by dx, which will become 2z. Sorry, dy by dz, which will become 2z into dz by dx. Okay. So that will be 2z into 2x. So you can see that this will become 4 times x square plus 1 into x. So that is 4x cubed plus 4x, which is what we would have got by expanding this and differentiating. But you can probably do this with less number of steps now. Okay. Doing the first question by quotient rule will be unnecessary because it will just make it more lengthy. So it's obviously going to be simpler by just writing this as x minus 2 by x. So just because I have another method doesn't necessarily mean I have to always use that. Sometimes it can complicate things, sometimes it can simplify things. So that's a matter of judgment where to use which method. Anyhow, just go through this once and let me know if there's anything you want to discuss in this. Otherwise, we'll come directly to worksheet 3, which is the latest one. Okay, good. So I'm assuming you people have done all this. Okay. So as I said again, make sure that you have the solutions of these questions worked out in proper detail in a notebook, okay, in serial order in such a way that you can refer to it in future. And also you can submit it when we ask you for the submissions. Okay. Just give me a moment. We'll discuss the third worksheet. Okay, let's come to this. Any doubts in the first question, any of the parts? Please let me know if there's a doubt in any of the parts in the first question. Okay. Yeah, Kirti, I'll come to that. Okay. Okay, second question. Anything here? Just one point that elaborate about this question. Here you don't actually need to do any differentiation. You can see that this implies that y is equal to 1 because of the trigonometric identity. So automatically you can see that dy by dx is 0. You don't need to differentiate that complicated lengthy function to actually show it, because the function is actually very simple. The identity is that sine square x plus cos square x is 1 for all values of x. So obviously dy by dx is equal to 0. Okay, let's come to this part. So I think this was a question we just discussed a while back. Okay. In this, you can use quotient rule or you can use product rule also. You can treat it as 1 by x into ln x. In this one, you will have to, in the E part, you will have to use the quotient rule. There's no other option. Okay, now unfortunately, there were two question threes. I labeled it wrongly. So the first of the two question threes, if there's any doubt, let me know. The second of the two question threes are rather easy. Okay, so I'll just put it here. So it was given to us that y is equal to root z and z was equal to this type of function. I think it was x cube plus x square or something like that. X cube plus 3x square plus 2x. Plus 2. Okay, so when you want to express y as a function of x in this, you have to just connect these two. So you can see that y is equal to square root of x cube plus 3x squared plus 2. And then you just apply your normal chain rule concepts and all that. So you can see that dy by dz is the differentiation of root z. So it will become 1 by 2 root z. Okay. And dz by dx is the differentiation of this cubic function, which is 3x squared plus 6x. Right? And for chain rule to find dy by dx, you just multiply these two things and resubstitute. So all that is done. Substitute x as 1, you will get the value of dy by dx. Okay. So this is also quite simple. Okay. So come to the fourth question. Just small misprint over here. This should have been 2 pi. Okay. So this term is 2 pi by 3 angle. This is actually equal to 120 degrees, as you know. Okay. The same over here. This is 2 pi by 3. Okay, so let's come directly to the fifth question then. So let's look at the information given in the fifth question first. Then we will discuss about how to solve it. So once again, it's like a practical application of. Achha, fourth question, last part, equation of tangent. Okay, we'll come to that. Let's discuss that. So by the time you do the graph of this and all this, you'll realize that the graph of y is equal to sine square x. After plotting the values and all, will come out something like this between 0 and pi. Okay, now we have to find the equation of tangent at the point x equal to pi by 4. So first of all, let's see the point x equal to pi by 4. So that's here. What is the value of y at this point? You can see that x equal to pi by 4, y is equal to sine square pi by 4. So that is half or 0.5. Okay, so this point over here, let's say the coordinates are a comma b. Those coordinates are pi by 4 comma 1 by 2. That is that point. Okay, now we have to find the equation of this line, which is the tangent at that point. This is the tangent at that particular point. So we can see that from this function, you had earlier got the rate of change as 2 sin x cos x, which by the way, you can also simplify and write it as sin 2x. Are you familiar with this formula?
No, sir.
No, sir.
It comes from this property in trigonometry that sin a plus b is sin a cos b plus cos a sin b. So from that you can show that sin 2a comes to be 2 sin a cos a. Okay. At this stage, if you don't simplify it, also it's fine. You can just leave the answer this way. It's okay. But if you simplify it further, it reduces to this. Okay. So anyway, so now we want to find the equation of tangent at this point. So this is the general, derivative of the function. The derivative is dy by dx. So at this point, at x equal to pi by 4, the slope of the tangent, what will be that? That will be the value of the derivative at the point pi by 4. That is the slope of the tangent, right? So the derivative is this much. It is 2 sin x cos x. So this one's value, the slope will become 2 times sin pi by 4 cos pi by 4. So that when you calculate, you will see it will come out to be 1. Okay. So this tangent is having a slope equal to 1. So clear so far, Bhavika? These two things are clear. The coordinates of the point where we are drawing the tangent and the slope of the tangent, these 2 points are clear, no?
Yes, sir.
Okay. Now you go back to coordinate geometry and you understand how you find the equation of a line which is passing through a point like this and having a slope of m equal to 1. So the equation of the line becomes like this, that y minus b is equal to the slope times x minus b. So now just substitute these things. Okay. So y minus half 1 into x minus pi by 4. So you can see the equation of this line will become like this. Y is equal to x plus 1 by 2 minus pi by 4. And that 1 by 2 minus pi by 4 is actually a constant in itself. So it is equal to y is equal to x plus some constant. So the slope is 1 and the y-intercept is actually half minus pi by 4. And further, you can also simplify pi by 4 as 3.14 divided by 4 approximately.
Okay, sir. Thank you.
You can understand now. Okay, so now let's come back to question number 5, the gas pump question. Okay. So let's understand the wording of the question first. So we have a cylinder which is initially empty at time t equal to 0, but we are pumping in gas, okay, at the variable rate like this, and this is given in gram per second. So this is a mass rate. Okay, so we'll consider, like, let's say this is our cylinder. Okay. Now at t equal to 0, the volume of gas is 0. Okay. V is volume of gas, but then we start pumping in gas. So let's say there's a gas pump through which we are pumping in gas from somewhere. So gas is pumping in, and also there is a leakage simultaneously. Okay. From the beginning only there's a leakage also. So what we can see is that now we can use proper rate of change concept. The rate at which volume is changing will be equal to the rate of the pump at which it is pumping in minus the rate of leakage. This makes sense, right? This is a logical statement. The rate at which the volume is changing is the rate at which volume is entering because of the pumping in process minus the rate at which the volume of gas is going out from the cylinder because of the leakage, right? So this is clear. So now this is a variable rate. This at a time t, the instantaneous value at t equal to t, this is equal to 4 plus t. So for example, at 0 seconds, it was 4 gram per second. At oh sorry, it's given in grams per second. So we'll take mass. It's given as a mass rate. Okay, we'll just change this variable to mass. So we'll consider the rate at which mass of gas is changing. So mass is a function of time such that mass is equal to 0 at t equal to 0. So this is a variable quantity. So the instantaneous rate of change of mass is the rate at which the inflow is happening minus the rate at which the leakage or outflow is happening. So that is equal to 2 plus t in grams per second. This is the instantaneous value of dm by dt. So this part is clear, people? Okay. Now let's see how we'll use this information to solve the rest of the question also. The first part we've got. So the net rate at which the mass of the gas increases with respect to time. So that is this only. So this is 2 plus t. It's a variable rate. So as time is progressing, the rate of increase of mass is also increasing with time. Okay, so just go through these steps and make sure this is clear. Okay, now let's use this information for the next part of the question. So first, let me write down the information that we got from there. First of all, we had the information that m was equal to 0 at time t equal to 0. Okay, m was such a function of time such that its value was 0 when t was equal to 0. And then we also got dm by dt was equal to 2 plus t in gram per second. Okay, so now we can understand that what type of function it is. It is a function whose derivative is this. Okay, so the derivative of the function is linear with respect to time. It's linear with respect to time. So that means the function itself should be what type? It should be a quadratic function. because we know that when we differentiate any power series or any polynomial, the derivative has the degree 1 less than the polynomial itself. So if the degree of the polynomial function was n, then the derivative should have a degree of n minus 1. So that n minus 1 is 1 because it's a linear function. So n must be 2. So the degree of this polynomial function must be, okay, so this must be a polynomial of degree 2 because this one, its derivative is a polynomial of degree 1. Okay, so n minus 1 is equal to 1. That's why n must be equal to 2. Okay, so now what we'll do is we'll assume, so mass as a function of time, let's assume that that mass is some at square plus some bt plus c. So all we have to do is we have to find the values of a, b and c, which are 3 constants. So to find them, we have 2 pieces of information. The 2 pieces of information we have is, one is this, and the other information we have is this. Okay. So try to use these 2 pieces of information to find out the unknown quantities a, b and c, and then from that obviously we'll get the final answer. Okay, so just try to work this out from this point onwards. Okay. I'll give you the full solution in a minute. Okay, so let's see how we'll use these conditions now. Okay, so from this, we'll get dm by dt as differentiation of this. Okay. So just differentiate this, treating a, b, and c as constants. So it is 2at plus b. Okay, that's the differentiation. Now compare this with this equation. So we have 2 plus t is b plus 2a into t. So from this, what we are getting, that b is equal to 2 and a is equal to half. And now what about c? So compare this equation with this thing here. So m is equal to 0 when t is equal to 0. That means c is equal to 0. So you got a, b, and c all three. So from that, now we know that this mass as a function of time will become 1 by 2 times t square plus 2. That's how it satisfies this condition that mass is 0 at t equal to 0. And if you differentiate this, you can see you get this. It satisfies both these. So that's what we've got now. We've got mass as a function of time. And next part, we have to just plot the graph. Okay, so hope this is finally clear with this. So just visualizing the graph as the final step. Once we've got the fact that mass is like this, so to visualize the graph of mass with respect to time, you can take some values of time and check out the mass. So obviously t equal to 0, m was 0. T equal to 1 second, for example, m will become half plus 2. So that is 2.5 grams. Let's check at t equal to 5 seconds, for example. M will become 25 by 2, that's 12.5 plus 10. So that is 22.5 grams. Let's check at t equal to 10 seconds, for example. M will become 100 by 2, that's 50 plus 20. 70 grams. Let's check at t equal to 20 seconds. M will become 400 by 2, so that's 200 plus 40. It's 240 grams. Let's check at 30 seconds. M would have become 900 by 2, that's 450 plus 60. So 450 plus 60, 510 grams. So when we plot the graph, we can take these as guidelines For example, if this is 10 seconds, this is 20 seconds, this is 30 seconds. So you can see it's a very disproportionately sort of curving kind of shape. So if this is 510, then 240 would be somewhere here. Let's say this data point, this data point, and comparatively 70 would be less than 1/3 of this, so somewhere here maybe. And like that, at 1 second, 5 seconds, etc., we have got those values. So basically the shape will be something like this. It's a quadratic curve. You can see the slope is increasing. So you can see that the slope of the tangent here, that was at t plus 2. So for example, the slope at t equal to 0 is 2. The slope at t equal to 10 seconds, for example, is 12 gram per second. Okay. And like that, it increases. So you can see how the slope is also rapidly increasing. All right, so that's about this. Let's come to the exercises in module now. So any doubts from exercise 1 in the module? That's on page number 38, I think, 38 or 39. Just if you can turn to your module.
Sir, I have a doubt in question number 8 and 26.
Question number
8 and 26.
8 and 26. Okay, let's.
Sir,
So
I have a
question
doubt
8.
in the 9th one also.
9 one also. Okay. So these questions, they are just like there to trick you actually. There's nothing difficult in the question. Tell me what is the quantity A over here? What kind of quantity is it? Is it a constant or is it a variable?
Constant.
Yeah, so just treat it like a constant. So when you differentiate it, this is just like 1 by a cube minus 3, which is basically a constant, into this function. No? Understood now? No? So when you're differentiating, take the constant outside and differentiate this function. So derivative of x square is 2x, derivative of x is 1, and derivative of 0 is, 1 is 0. So got it now? So you don't have to use quotient rule. You're understanding my point?
Yes, sir.
Okay. If you use quotient rule also, you'll get the same thing, but after a lot of effort. Okay. So you just have to understand that this whole denominator is basically a constant. It's not a function. So we don't need to use quotient rule. Same with this also. This root pi is a constant. Okay. So in the 9th one, just treat the function as a constant multiplied with 1 minus x cube. And what is that constant equal to? That constant is equal to 1 by root pi. Is it clear, beta?
Yes, sir.
So 1 minus x cube
3x
derivative
square
is
by pi.
minus 3x square. No? So the derivative will just become minus 3x square into that constant, which is 1 by root pi. So this is just a trick question, nothing else in this. Okay. This 5th question, of course, is quite lengthy. So in this, again, you will have to use separately, you differentiate this term by using quotient rule, and separately you can differentiate this term by using product rule, or you can even open the bracket or whatever you like, and then find out the derivative. Okay, so anything else from section 1? We'll come to section 2 also, but Okay, then let's come to section 2. Somebody had a doubt, I think, right? Anything here between 10 and 23? Okay. Let's come to section 3. Okay, question 27. All right, let's take a look at that. So question 27 is again, we'll treat it like a composite function. Y is a square root of ln x. So take your dummy variable as the term inside the square root. So that's ln x. So y becomes square root z. Okay. So the next step for us after this now becomes the chain rule step. Okay. So dy by dx. So derivative of root z is 1 by 2 root z. Okay. And derivative of ln x is 1 by x. So then finally resubstituting z as this, we get 1 by 2x square root of ln x. This becomes our dy by dx. Okay, anything else in this section? Okay. Just again to reiterate a point, again questions like this, if you see the 20th one or the 21st one, you'll have to use chain rule twice. I mean, in this you'll have to use chain rule twice, in this only once. So differentiate this, that is simple, is minus sin x. But when you're differentiating cos cube x, you have to use chain rule. Okay. So think of that as a new variable. Z is equal to cos cube x. So you can take z as u cube, where u is equal to cos x. And then you can find dz by dx, like we did in that question earlier, as dz by du into du by dx. So dz by du will become 3u square, and du by dx is minus sin x. So this becomes minus 3 sin x cos square x. That term becomes like this. So this second term's derivative will become minus 1 by 3 into this. And the first term's derivative is minus sin x. Similarly, for this also, differentiate sin square x separately, sin cube x separately, and then use that in this. Okay, so these are just a matter of practice and learning to apply the different properties in different patterns of questions. Okay.
So can you show question number 26?
Sorry, which one? Question number?
26.
26. Okay. So 26 is, again, it's a question where we have two options, because we can also use a property of log. Y is equal to ln of x square. One option that we have is we can use this property of log, that log for any base of a to the power n is equal to n times log of a to the base same one. So we can use that property over here. So this can be written as 2 ln x. So once I write it as this, it makes life very simple, because that will just be 2 into 1 by x or 2 by x. Okay. The other option is, if I don't use this property, then I can always use chain rule. Okay. So in that, substitute z as x square. So y becomes ln z. So now dy by dx becomes, by chain, becomes derivative of ln z, which is 1 by z, into derivative of x square, which is 2x. So that again, by resubstitution, you can see that is 2x by x square, or 2 by x, which is the same as 1 by x. Whereas this thing is different. This is ln x is whole square. Okay, so here also you have to use chain rule, but you will have to take this as z square, where z is equal to ln x. So three variations of composite functions using the ln operator. Okay, so I hope these are clear. Now, anything from exercise 3? Anybody has a doubt? Have you started working out the questions which I gave from exercise 3? Okay, so let me give you a bit of an idea of what is the approach for these type of questions. Okay. They are application of differentiation or application of derivative in practical type of questions. So let's understand how that works. So in all these type of questions, now we have to basically use chain rule. It is a practical application of chain rule type. For example, if you see the first question in this, as you're heating the disk, what is happening? The radius is increasing, and as a result of that, the area is increasing. So what we have to do in this is, first of all, we have to express the area as a function of radius. Okay. And radius is changing with time. So it's a function of time. So dA by dt, the rate of change of area with respect to time by chain rule, will come as rate of change of area with respect to radius into rate of change of radius with respect to time. So this is the concept we have to apply in these sort of questions. Okay, so let's look at a variation of these type of questions. I'll give you another question to practice out. So suppose we have a metallic plate like this, which is a square of dimension L by L. Now it is being heated such that its length, side length, is increasing at a uniform rate. The rate at which the length is increasing, that is suppose 0.2 millimeters per second. Okay. So now let us say at a certain instant, L is equal to 10 centimeters. So find the rate at which its surface area expands at this instant. And again, we'll also find the rate at which the surface area expands at an instant 10 seconds later. Let's work out this question now. So try to work out the first part and send me the answer. Yes, very good, Anirudh and Shubham. Be careful of the units as you are doing the calculation. Okay. So again, the concept here you can see is that area depends on length, and length is some kind of function of time because it's changing with respect to time, such that the rate of change of length is equal to 0.2 millimeters per second and constant, or we can write it as 0.02 centimeters per second. So now when we want to use this information to find the rate at which the area is changing. So for the first part, so in general, we can see that only thing we have to understand here is that L is a variable, it's not a constant, it's changing with time. So this is 2LDL. So this is how we have calculated the rate of change of area with respect to time using chain rule. So for the first part, we have to just find out dA by dt at some instant, let's say t, when L is equal to how much? L is equal to 10 centimeters and dL by dt is 0.02 centimeters per second. So that will become that's why I said you have to be careful about the unit. You can of course express this in millimeter square per second also. Now the second part, you want to calculate this at an instant which is this time plus 10 seconds. So at this point of time, what will happen? What will be the length? So you can see that the length is increasing with time at a uniform rate. Now, look at length versus time. So at some particular time, we track the length was 10 centimeters. Okay. Now we are looking at a time which is 10 seconds later. So at this point of time, the length would have become 10 plus some delta L. So for that, we know the slope of this is 0.02 centimeters per second. Okay. So we can see that delta L by delta T is equal to the instantaneous rate, which is a constant. Okay. So in this case, the delta L divided by the time interval of 10 seconds. Okay. So the change in length by now, it has become 0.2 centimeters. So this length at this point of time is 10 centimeters plus 0.2 centimeters. So it is equal to 10.2 centimeters. Okay. So this new value of rate of change of area at this time will become 2L, that is 2 into 10.2 into dl by dt. This much in centimeters square per second. Yes, very good. Anirudh, that's correct. So this becomes the answer of the B part. Okay, so before we conclude this now, I'll also show you something interesting. There's a logical way also to understand this rate of change of area instead of the calculus method. So if we compare a square plate at two different times, but for a very short interval of time. So this is the situation, it is at time t equal to t. Okay. Now let's consider, because of the heating, the dimension of the plate has just slightly increased. Okay. So imagine that this is actually only slightly different. So it's increased from L by L. Is this. So now it's increased to L plus DL. So at T equal to T plus dt, area has become E plus dA, because length has become L plus dL. So this new value of area, you can see, whereas the original value of area was L square. Okay. So you want to find out dA by dt from this. You can see that in the diagram, the area which is increased is this shaded portion. If you look geometrically, you can understand that the change in area is basically equal to, now this thickness is dl. Is it? Is it correct what I've written, that this thickness is dl? No, it is dl by 2. Okay. Because see, this whole thing is L plus dl. No? So on each side, it's increased in thickness like this. Okay. So what is the shaded area? It is 4 times L into dl by 2. Okay. So it is 2 times L into dl. That is the increase in area geometrically. Similarly, if you do algebraically, you can see that by subtracting the two equations, so by subtracting these two equations, you can see that dA okay. Now dl whole square will be negligible compared to 2LDL. So we can approximate this as 2LDL, because dl whole square will be very small compared to 2LDL, because it's a differential change. So algebraically also you can see that the change in area is like this. Geometrically also we can see the change in area is like this. So rate of change of area what we had understood by application of chain rule of differentiation, also understanding it by a geometrical sort of method or by a logical sort of method like this. Okay, people, so hope this is clear. So to solve exercise 3, we have to use some common sort of, volume and area type of formulae to For example, volume of a cube is L cube, volume of a sphere is 4 by 3 pi r cube, volume of a cone, okay, of a symmetrical cone is 1/3 of pi r square into h, where h is the vertical height. Okay. Surface area of a sphere is 4 pi r square. So these are some of the common formulae that you'll be using in solving those type of questions. Okay. But other than that, it's basically the application of chain rule this way. So with this, we come to a conclusion for today's class, people. Wish you all the best and thanks for attending. Hope all your doubts are cleared thus far. If you're solving at home and anything else comes up, you can always send me a WhatsApp message so that you can clear the doubt then and there. Okay. And of course, you'll have a doubt session in the weekend also again. So that's it for today, people. Wish you all the best. Next time, we'll be discussing more about application of differentiation, especially to understand behavior of functions, things like maxima, minima, etc. before we come to integration eventually.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.